Good morning, everyone. Today, we delve into a groundbreaking study titled, "An Image is Worth More Than 16 times 16 Patches, Exploring Transformers on Individual Pixels." This research challenges the conventional use of locality in vision models by employing transformers to process each pixel individually. It aligns with the evolving philosophy of deep learning, shifting from fixed priors to dynamic, data-driven models. Prepare to explore how this approach could revolutionize our understanding and capabilities in processing 2D images and potentially beyond. Let's get ready to uncover some intriguing insights. Let's delve into the key highlights of our research. The primary motivation behind this paper was to challenge the traditional necessity of locality in vision models. We explored the capabilities of transformers to handle individual pixels directly as tokens, aligning with the deep learning philosophy of replacing set priors with learnable alternatives. This approach questions whether the locality bias, which has been a staple in vision models, is truly essential. Addressing this problem, we introduced the pixel-wise transformer, or PyT, proposing it as a flexible and scalable alternative for image processing architectures. This model allows us to rethink how we handle image data, offering a potentially more versatile framework for various vision tasks. By treating each pixel as an independent token, PyT removes the constraints imposed by locality and opens up new possibilities for model architecture and image representation. Let's delve into the core aspects of our research, focusing on the innovative approach of pixels and transformers, or PyT. This method revolutionizes how we handle visual data by processing individual pixels directly with transformers, treating images as unordered sets of pixels. This allows the model to autonomously learn spatial relationships from the data, a significant shift from traditional methods that rely on predefined spatial biases. Our findings reveal that transformers are not only capable of managing individual pixels effectively, but also demonstrate that removing the locality bias can lead to more versatile and scalable architectures. This is pivotal as it challenges the existing paradigms in vision model architectures and paves the way for new design avenues in vision models. Through rigorous empirical testing, we verified the effectiveness of this approach. Our work not only underscores the potential of transformers in handling fine-grained visual information, but also opens up exciting possibilities for future architectural innovations in the field of computer vision. Let's delve into the key results from our exploration of PyT, or pixel-level transformers. Our findings are quite promising, showing that PyT can effectively handle individual pixels as tokens. This suggests that focusing on resolution and pixel-level modeling could be more critical than previously assumed locality in image processing. It's important to note the experimental nature of PyT, which underscores its potential for further exploration and refinement in future research. These insights open up new avenues for understanding and developing advanced models in the field of computer vision. As we delve into the transformative approach of the pixel transformer, or PyT, let's first understand its foundational concept. Traditionally, vision models have heavily relied on convolutional neural networks, which inherently assume that pixels close to each other are more related than those further apart. This assumption, known as locality, has been a staple inductive bias in image processing. However, PyT challenges this norm by treating each pixel in an image as an independent token, similar to how words are treated in natural language processing. This is visually represented in the figure on this slide, where you can see the PyT model architecture. Notice how it eliminates the locality bias by using learnable position embeddings, allowing the model to consider each pixel separately yet effectively. This shift not only simplifies the architecture, but also enhances its flexibility, enabling it to adeptly handle a variety of tasks across different image sizes and types. This marks a significant step forward in our quest to develop more generalized and efficient models for visual data interpretation. Let's delve into the core of our investigation, starting with the identification of a significant problem in existing vision models. Traditionally, these models have relied heavily on the concept of locality, which assumes that pixels close to each other are more relevant for understanding the image. This assumption might cause us to miss finer details that become apparent only when we consider each pixel individually. This brings us to the motivation behind our study. We aim to challenge the traditional reliance on locality by exploring the capabilities of transformers to process individual pixels directly. This approach is unconventional, as it contradicts the established norms that have guided the development of vision models for years. Understanding and addressing the limitations imposed by locality is crucial. It opens the door to creating more versatile and powerful models that can potentially transform the field of computer vision. By breaking free from these constraints, we can develop systems that not only perform better, but are also more adaptable to a variety of visual tasks. Let's delve into a novel approach in the field of computer vision, introducing pixels and transformers, or PyT. This method processes individual pixels directly with transformers, challenging the traditional need for locality bias in vision models. By treating each pixel as a separate token, PyT eliminates the assumption of spatial relationships within the architecture, allowing the model to learn these relationships directly from the data. Key innovations of PyT include its ability to handle each pixel independently, which significantly reduces the complexity of input data handling and increases the model's flexibility. This approach contrasts sharply with conventional methods that rely on predefined spatial hierarchies or patch-based processing. The expected improvements from adopting PyT are substantial. By directly manipulating pixels, the model can potentially offer enhanced versatility and performance across various image sizes and types. This capability could set a new standard for future designs in vision models, influencing how we approach tasks that require detailed image understanding. In our exploration of the PyT, or pixels as tokens model, we challenge the traditional approach of locality in vision models by treating each pixel in an image as an individual token. This fundamental shift allows the model to learn spatial relationships directly from the data, rather than relying on predefined assumptions. The architecture of PyT is built on the robust framework of transformers, consisting of n layers. Each layer is equipped with a self-attention block and an MLP block. To ensure stability and enhance performance, we incorporate layer norm and residual connections throughout the structure. This design not only supports the unique processing of pixel tokens, but also scales effectively with the complexity of image data. By rethinking how pixels are treated, PyT opens new avenues for understanding and processing visual information in machine learning models. In our proposed research, we delve into the technical details of the PyT architecture, focusing on two main components: input representation and the elimination of locality inductive bias. Starting with input representation, PyT transforms pixels into a higher dimensional space through linear projection. This process incorporates a CLS token for classification purposes and utilizes learnable position embeddings to enhance model performance. Moving on to a critical aspect of our architecture, PyT challenges traditional design by eliminating the locality inductive bias. Unlike convolutional neural networks and the standard vision transformer, which rely on fixed spatial hierarchies, PyT is permutation equivariant. This means it does not assume any inherent spatial relationships among input features, allowing for a more flexible and potentially scalable model architecture. These innovations mark a significant shift from conventional approaches, setting the stage for more adaptable and robust vision models. Moving on to the technical details of our research, let's delve into the training process. Our models, including PyTB and VTB, were rigorously trained on the ImageNet dataset using supervised learning techniques. We focused on traditional metrics such as classification accuracy to evaluate their performance, ensuring that our findings are robust and reliable. Addressing the computational considerations, we acknowledge the quadratic complexity inherent in our models. This presents a significant challenge for practical applications. However, we are actively exploring future directions that could potentially mitigate these computational demands, making our models more feasible for real-world applications. On the visualization front, we have developed methods to illustrate what PyT learns about pixel-level features. These visualizations not only provide fascinating insights, but could also influence future designs of vision models, pushing the boundaries of what's possible in image processing. Lastly, for those interested in the algorithmic backbone of our work, we provide a detailed breakdown of our novel algorithms, complete with mathematical formulations and pseudocode. This detailed exposition aims to make our methodologies transparent and accessible, fostering further research and innovation in the field. Let's delve into the technical results of our study, where we rigorously tested the PyT model's unique approach of handling individual pixels as tokens. Our experimental setup utilized the ImageNet dataset, a standard benchmark in the field of computer vision. The primary goal of these experiments was to evaluate how effectively PyT can process these individual pixels, challenging the traditional necessity for locality bias in image recognition tasks. The results were quite revealing. PyT not only managed to handle pixels independently, but also demonstrated that it could achieve competitive accuracy when compared to traditional vision transformer models. This is particularly noteworthy given that PyT is still in an experimental phase. These findings underscore the potential of PyT to revolutionize image processing techniques by eliminating the reliance on predefined spatial relationships, thus opening new avenues for model architecture in computer vision. Moving on to our technical results, we delve into an ablation study that scrutinizes various configurations of the pixel-level transformer, or PyT. We experimented with different layer depths and tokenization strategies to understand their effects on model performance. Our findings reveal that deeper models and more refined tokenization approaches significantly enhance performance. This underscores the scalability and adaptability of PyT, highlighting its potential in handling complex image processing tasks. Furthermore, these results validate our initial hypothesis that transformers can effectively manage individual pixels without relying on traditional locality-based methods. This breakthrough challenges the conventional necessity of spatial proximity in image processing architectures. By demonstrating that data-driven learning can effectively replace manually set inductive biases, we open new avenues for designing future vision models that are both flexible and powerful. As we delve deeper into the capabilities of PyT, extended training periods reveal that PyT benefits more significantly over time compared to DT. This suggests that PyT possesses superior long-term learning capabilities, adapting more effectively as training progresses. We also observe how the duration of training and the complexity of the dataset influence PyT's performance, providing valuable insights for optimizing training strategies in future research. Turning our focus to the visualization and interpretation of what PyT learns, we present visual outputs that illustrate the model's process when handling individual pixels. These visualizations not only shed light on the model's learning mechanisms, but also enhance our understanding of how transformer models can be interpreted within vision tasks. This is crucial for advancing our ability to decipher and trust the decisions made by these powerful models. As we conclude our presentation, let's recap the key contributions of our research. We've demonstrated that transformers can effectively process individual pixels as tokens. This finding challenges the traditional reliance on locality in vision models and introduces a new perspective on how we can approach image processing tasks. Our introduction of the pixel-wise transformer, or PyT, offers a scalable architecture that operates without the need for locality-based inductive biases. This is a significant step forward, as it aligns with the deep learning community's goal to replace manually set priors with data-driven, learnable alternatives. These contributions are pivotal, as they not only enhance our understanding of transformer capabilities, but also open up new possibilities for future research in handling 2D images and potentially other domains.